Hello, my name is Elsa Angelini, and it's my great pleasure and honor to have been invited today to give a keynote presentation on a project that we've been working on for the past 10 years at Columbia University, looking at unsupervised learning and domain adaptation for subtyping of emphysema on very large cohorts of lung CT scans. So to start with some background information, we are looking at the respiratory system, and in particular emphysema and association with chronic obstructive pulmonary disease, or COPD. COPD is the fourth leading cause of death in the world. It affects 16 million of subjects in the US, and emphysema corresponds to destruction of the alveoli walls, those small units here in charge of gas exchange. Emphysema is smoking related, it's age related, but it's also genetic related. And the exact mechanisms for developing emphysema remains mostly unknown. So the baseline hypothesis for all this work was that lung texture learning for emphysema subtyping can advance COPD disease understanding. So we're using computed tomography, CT, scans to look at the lung structures. And those are acquired in the single breath hold, which is enabled by modern CT scanners. So those are very large image files with a submillimetric resolution, large matrix size, and intensity values which are calibrated in Hounsfield unit, but which are also in a very large range of values, from negative to positive. So if you talk to clinicians, they tell you that, well, you have 40 megavoxels of lung tissue to look at in a single scan, and that should enable in vivo study of lung structure and disease patterns. And in particular for emphysema, this is an illustration here of a subject where you can see those small pockets of air, which corresponds to regions of emphysema, and this can be small like this, or this can be much larger, as in this example here in the bottom. So quantification of emphysema has been done for years by clinicians, and using a very simple approach based on the histogram of the scans, and they typically would use thresholding at a fixed value, for example, minus 950 Hounsfield unit, to compute what we call percentage emphysema, which is the percentage of lung that is below this threshold value. Sometimes people also use things a little bit more sophisticated, like percentile density, to define the threshold based on the individual CT scan. In parallel, subtyping of emphysema is also an old idea and has been defined at autopsy, leading to three very standard, what we call standard emphysema subtypes that have been used a lot in the clinical world, and those are called the centrilobular emphysema, the panlobular emphysema, and the paraseptal emphysema. Unfortunately, when you ask a radiologist to score or to localize this type of emphysema on an individual CT scans, there's very limited inter-rater agreement. So this project all started with the data, and basically clinicians at Columbia University coming to us and seeing if we would be interested in collaborating and working on emphysema subtyping, given the very large cohort they had access to as being one of the screening center for the acquisition of those images. So those cohorts are called MESA, Spiromics, and MCAP. MESA stands for Multi-Ethnic Study of Atherosclerosis. Spiromics stands for Subpopulation and Intermediate Outcome Measures in COPD. And MCAP, which is a smaller, older cohort, stands for Emphysema of Cancer Action Program. So that's the initial table of data we were working with. And you can see the different studies here. The number of patients with CT scans, total number of CTs, etc. One thing to note is that MESA is what we call a non-disease cohort, as it didn't focus initially on lung disease, and there are a significant number of non-smokers recruited in this cohort, while Spiromics is a disease-specific cohort which enrolled people who smoked more than 20 pack years. The other thing to notice here is that both cohorts here have GWAS data enabling genotyping of any markers we would discover on those data. So as a start, when you balance the positive and the challenges, aspect. On the positive aspect, those are massive prospective and longitudinal cohorts with a follow-up of up to 10 years in MESA, and here 3 years at that time in Spiromics. It's multicentric, which is really good for machine learning. Those are standardized CT protocols with quality control, which means basically this is the best you can hope for in terms of lung CT scanning. Data comes with state-of-the-art quantitative clinical measures of respiratory symptoms. And the lung and the airways were segmented by a single reading center, which is also good to have some systematic reading by a single center. On the challenging side, well, it represents 10 years of CT scanner generations, and this technology evolves quite a lot over the years. This means also that even for a single generation of CT scanner, you have multiple scanner types to deal with. And when you deal at this level of numbers of CT scans and participants, there's always a huge effort for database management. And finally, you get into MESA and Spiromics governance, and which I will talk about in the next slide. So overall, 11,000 full-lung CT scans, 35,000 cardiac scans for over 12,000 participants over up to 10 years of follow-up. So when you want to work with MESA and Spiromics data, you basically enter what I would call a multicentric cohort ecosystem in the sense of a complex network or interconnected system. And you can, both cohorts have a public website with a lot of very interesting information. And as you can notice, they also have some tabs here, which are called publications and ancillary studies, and the same here for Spiromics. And those two tabs are basically governed by two different committees, the Publication and Presentation Committee and the Ancillary Studies Committee. So the first thing you need to do if you want to do any kind of analysis on those cohorts is to get some ancillary study approved, which means you need to write a mini grant, mini proposal with quite detailed strategies on terms of your hypothesis, what you want to look at, and how you want to look at it, and what type of outcome and advancement that would lead to. And if you want to submit that for funding, for a grant call, you need to be basically prepared 8 weeks before the deadline. So your whole calendar is completely shifted, and you live in a kind of a very different schedule as anyone else. And also, whenever you want to write a paper, you also need a paper approval. And if you want to submit a paper to a conference with a specific deadline, your calendar is also shifted by several weeks ahead of the deadline, so that you get your manuscript or even your abstract approved by the specific committees. The other thing too, which is a little bit of a constraint, is that it is your responsibility to avoid any overlap with manuscripts already in progress or published, which means if you want to replicate a study that has already been done, you need very good reasons for that. And you need to convince the committee that you have a good reason. And finally, you need to have all co-authors approving and having seen and approved any proposal you submit. So you cannot include any last-minute co-authors in this kind of ecosystem. So when we started about 10 years ago, the first thing we looked at is what's the current state of the art in terms of quantitative emphysema analysis on CT scans. And basically there were no emphysema segmentation tool available. The machine learning was only done in a supervised fashion, mostly by a group in Netherlands. We had a feeling that spatial localization would matter, as we knew from even the standard radiologic emphysema subtypes that there were some different prevalence in different regions of the lung. And there were other cohorts also emerging in the field of lung CT scans, in particular around interstitial lung disease, and also the COPD gene, which is another massive cohort with lung CT scans. Right. On the other hand, we also had to think ahead about using cardiac CT scans to look at the lung, which might sound like a crazy idea, but not to the clinicians who already had a paper published in Academic Radiology showing that, or claiming that you could look at personal emphysema at population level with a very good accuracy on cardiac CT scans, even though you have degraded resolution and you could see only 2/3 of the lung region. And this was anyhow critical for us to aim for the same type of analysis on cardiac CT scans, because most of the scans we were given were actually cardiac scans, and that was also the only option for us to perform longitudinal studies over 10 years, which was really the goal of the collaboration. There are some extra data that come again with those CT scans. Lung masks were provided by Vida. Emphysema, of course, masks were available by just using simple thresholding. We also had some visual annotation of standard emphysema subtypes on a subset of scans, which was done by one of our clinical collaborators. And also, at some point, we were given upper limits of normal in person emphysema values, which were basically adjusted individual reference value of the expected or the normal percent of emphysema for a given person, taking into account covariates such as height, sex, height, race, ethnicity, BMI, and age. So based on all that, the second hypothesis here is that emphysema is common in the general population in the absence of COPD, which was a really good news for us because we had to start working with the MESA cohort, which is again the non-disease cohort in terms of emphysema. And as shown here, if you look at baseline scans, the person emphysema in those scans has a median value of only 18%, which reduces quite a lot the number of voxels of interest in the CT scan, but which is still quite reasonable. So, having all that and discussed with the clinicians, the mission that we were given is to study and seek purely radiological emphysema subtyping, which means we had no access and no use of any demographic or clinical measures. But of course, we had information on scanner type and or reconstruction filter type that were used per scan. So to conclude on this background information, the first thing we had to do is to develop our own emphysema segmentation tool, which would be really reliable at the individual level. We did that using a hidden Markov measure field, and we called the associated person emphysema the HMMF person emphysema. And so it's a statistical method and leading to pixel-wise labeling of emphysema, and which was published here. And one of the things that took us a lot of time is actually the parameter tuning, especially for the spatial regularization, which is illustrated here, as image quality again can vary a lot, even for the same subject scan with 2 CT acquisition using different reconstruction filters. So without any ground truth, the thing we looked at is the evolution in time of the person emphysema at the individual level to see if our approach would seem to be provide robust measures and plausible measures of progression of emphysema in time. And as you can see here, our measure grows steadily over years between 2004 and 10, while thresholding can show a lot of variation and especially decrease in emphysema measurement if you change scanner type. And the one interesting thing that we saw here is that if you do a little bit of Gaussian smoothing prior to thresholding, that stabilizes a lot your measure, even though it's still not really completely reliable. And so again, as a proxy of validation of our approach, we use normal subject here from MESA. And we showed that on the population level also, we had a very steady increase of emphysema over years using our segmentation method, and that the rate of increase corresponded to the clinical rate that is used as the reference by clinicians. So what we learned in this first phase is that CT scans vary greatly, despite what you can read in a textbook. That parameter tuning is key and can take a lot of time. Gaussian filtering can help in this type of data where you have lots of texture, but also quite some noise sometimes, and using normal cases was really key for us in this initial phase of development. Now moving on to the method section, I'll go over our strategy for spatial mapping, unsupervised learning, and domain transfer. So the development for unsupervised learning took about 4 years, spending the first year on, again, gathering, preparing, and learning the data, knowing that we only had images in our hand and that deep learning was not yet an option at that time. And we actually spent quite some time on agreeing on the best way to sample region of interest, RI, in the individual scans, knowing that it was not possible to use all emphysema RIs from all individual scans. Then we spent basically 3 years doing unsupervised learning and iterating very regularly with our clinical collaborators to discuss those subtypes and inspect them via, for example, looking at their appearance, their spatial prevalence, as illustrated here, and iterating with them so that everybody was convinced that the subtypes are plausible, are reproducible, and are meaningful. And that goes through, again, a lot of evaluation metrics such as measures of reproducibility, measures of association with clinical symptoms done by the collaborators, and also measures of association with the standard emphysema subtypes. Once we were all happy with our subtypes, we then moved on to handle the cardiac CT scans and being able to label emphysema subtypes on those scans, and this is where we use deep learning. And basically after 4 years, we were ready for the final end goal of the project, which is genetic association between emphysema subtypes and genes. And this is done via GWAS analysis. This is performed by an external collaborator. And so that, those analyses are really massive efforts. They need as many samples as you can, but in the thousands. And they are very costly to run. So basically, you only reach that stage once the clinicians are completely persuaded that what you have in hands and what you're proposing is really a solid biomarkers. So our approach, we started with standardized lung shape spatial mapping because we wanted to have access to spatial localization. And then we developed a two-stage unsupervised framework combining spatial and texture information. And finally, again, domain adaptation was used via adversarial deep learning to handle the cardiac scans. So regarding the lung shape spatial mapping, we used a very old idea of encoding shapes using Poisson equation. So having a lung shape here, we're segmented with a lung mask. We first define a patient-specific core position inside the lung, and then we use Poisson diffusion to encode every voxels in the lung with a radial coordinate that defines the distance from the core to the peel being the outside surface of the lung. And we also augmented that with two radial coordinates, theta and phi here, so that we also could encode the position in the anterior, medial, posterior, lateral plane, and also the inferior to superior plane. So this is what we call now Poisson distance conformal mapping. And this is actually really nice to have such tool to spatially align lungs without requiring any registration. And this is very analogous to what is done in neuroimaging to map brains on spheres. And just with this simple tool, we were able, for example, to generate first-time atlases of the lung. For example, here, just looking at the Hounsfield units of within scans. And on this small cohort of non-emphysema subjects, if you project the average intensity values in a normal population, you end up by visualizing very clearly what is known as the gravity effect, and which leads to having attenuation values in the anterior part of the lung with darkest attenuation values than in the posterior part of the lung. And from this normal population mapping, then we can also for example, generate relative intensity projections in emphysema population. And this is using the subcohort that was visually annotated by experts as being dominated by centrilobular, panlobular, or paraseptal emphysema. And again, there's lots of information here that you can evaluate. And for example, confirmation that the paraseptal emphysema has a preferred or darkest here with the darkest density prefer localization toward the pier rather than the core of the lung. All right, then the first step for the really, in the sense, the unsupervised learning was to encode regions of interest, ROI. So we used a cubic ROI of this size, and we equip each individual ROI with a particular sampling strategy inside the lung in terms of texture features and spatial features. The texture features were based on a Texton dictionary, while the spatial features, again, use the location encoding that I just presented in the slide before. And then we used a very classic, as a first step, a very classic clustering approach where we iteratively update a right assignment in an individual lung texture pattern, LTPs. So by minimizing a dedicated cost function, which is composed of three terms to constrain texture distance, to enforce spatial regularization, and to also enforce some texture penalty differences. We worked with an arbitrarily large number of LTPs in this first step, and here we chose just to work with 100 LTPs. Once we have those the centroids for those 100 LTPs, we move to step 2, where we define what we call spatially informed lung texture patterns, SLTPs. And for that step, we chose to use the InfoMap graph partitioning algorithm, which is fully unsupervised in the sense that it also decides itself on the final number of clusters. To encode the similarity between the nodes in the graph to be partitioned, we relied on a notion of replacements and saying that two LTPs are similar if they replace each other when one is removed out of the pool. Doing that, we moved from 100 LTPs to 10 SLTPs. All right, in terms of evaluation, once everybody was happy with this type of pipeline, what we did is use the spiromics, so the disease cohort that we first split into two subsets, which we call training set 1 and 2 here. And we learned SLTPs using those two subsets independently. So we end up again with a series of 10 SLTPs, which have some similarity, visual similarity, and also some similarity in terms of spatial prevalence, which is encoded here. And what we did for as a validation is to measure two things. One is the reproducibility of SLTPs across those two learning experiments, and we measured reproducibility at the regional level as a percentage of labeling overlap of test ROIs, and also at the individual level, measuring the correlation of SLTP histograms within individual subjects, and both reproducibility were super high. And finally, we also tested the ability to encode for those subtypes to encode the standard emphysema subtypes, which is very important in terms of clinical relevance, and intra-class correlation were very high for the three subtypes. Moving on, then we retrained again using the whole spiromics cohort now, and we decided that that would be our final SLTPs. So with those, which ended up again to be 10, we moved on and labeled all these individual scans in spiromics and in MESA, leading to those very nice maps, but also to histograms, which are a kind of signature of emphysema in individual subjects. And using those histograms, we performed some population clustering to see if we could maybe further reduce the number of SLTPs. And we actually did, and we moved on from 10 SLTPs to 6 quantitative emphysema subtypes, or QES. And those subtypes were reviewed also by collaborating radiologists who agreed with the aggregation of SLTPs and who also came up with nice names for those QES. So currently we have 6 QAS, which are called apical, diffuse, vanishing lung, senile, and 2 CPFE type. CPFE stands for combined pulmonary fibrosis and emphysema, and those 2 types are either restrictive or obstructive. Having those QAS, if you look at their distribution in the whole population, you can see that, well, you can see several things and comparing MESA and spiromics. First, you can see that some QAS are rare, and especially the vanishing lung is only observed in the disease cohort. The apical is also very prevalent in the spiromics, the disease cohort, while it's quite rare in the normal cohort. On the other hand, for example, the senile QAS is equivalently prevalent in the 2 cohorts, which tend to make sense. The second thing we looked at is the clinical significance of those QAS in spiromics and MESA, and that means measuring association of QAS with respiratory symptoms, physiology, and prognosis. So there's a lot of information here. This is for individual QAS here per columns. And the red shading basically indicates statistically significant association in the sense of worsening symptoms, while the blue and green shading indicates statistically significant improvement. And we also evaluated here association with outcomes such as hospitalization and mortality. So being done with the discovery of emphysema subtypes on full lung CT scan, we moved on to labeling those same subtypes on cardiac CT scans. And while everything looks good when you look at an axial slice of such cardiac CT scan, you immediately realize that when you look in the longitudinal direction that you've lost a lot in terms of texture resolution. And this is because of a factor of 5 in slice thickness between full lung and cardiac CT scans. So basically we were facing 3 challenges. First, we are missing the apical region of the lung. Second, we work with degraded texture. And third, we have to handle a very large set of scanner types, which varied a lot across several years. So how do we do the emphysema subtype labeling? Obviously, we can't work directly as before, and we need to be quite innovative here. So the first thing we needed is actually to detect where emphysema was present in those cardiac scans. And so we had to figure out a way to perform emphysema segmentation. And then once we have the emphysema voxels in those scans, to perform the labeling, we exploited deep learning and for domain adaptation. And this deep learning, basically the key idea for this deep learning was that we have full-lung CT scans with ground truth labeling of emphysema subtypes, and we generated synthetic cardiac scans to be able to have a supervised learning of the labeling and added to a domain adaptation so that what we were doing on those synthetic scans could be applied to the real cardiac CT scans. And at the end, we ended up with over 17,000 longitudinal cardiac and full-lung CT scans being labeled with emphysema subtypes. So scaling up a lot what we were able to provide for the final GWAS analysis. So first, regarding the segmentation, where we revisited the HMMF segmentation method, and we spent quite some time in doing parameter tuning for all the hyperparameters of the method. So for the full lung CT scan, as I mentioned, we ended up having scanner-specific parameters, especially to parameterize the statistical distributions used to model the emphysema and the normal lung tissue. And here for the cardiac scan, we came up very quickly to realize that we needed also to use some subject-specific parameters, especially for the normal lung tissue mean values, as it varies a lot between scanner types, and this is easily inferred by the outside air value in individual scans. So in terms of validation of this segmentation, again, we don't have any ground truth, so we exploited 2 things that was available in our data. First, for some subjects, we had 2 repeated cardiac scans acquired at the same visit. And that's really gold because you know here that whatever your segmenting should be highly reproducible. So we first looked at the population level reproducibility of percentage of emphysema measures. And here, this is again a nice confirmation that actually at the population level, if you compare personal emphysema in the first scan and the repeated one, any method being thresholding with filtering or HMMF, you get a pretty high reproducibility. But now if you look at the individual level, looking at the dice overlap, so really pixel-wise overlap of what you have segmented in the repeated scans, then HMMF made a big difference and led to a very significant improvement of the dice value compared to thresholding. And this is illustrated here on overlapping maps of emphysema voxels segmented using thresholding with Gaussian filtering, and again here the HMMF where you almost see green true overlap pixels basically, and very little disagreement. The second thing we did as an evaluation is to exploit the fact that we had longitudinal cardiac scans in exam 1 to 4, and versus and then a full lung scan in exam 5. And so we looked at the pairwise correlation value on those longitudinal scans within a very short time period of 18 months, and among normal subjects where you expect a very small increase in personal emphysema. And this is what you can see here is that the baseline cardiac exam and the follow-up exam, cardiac exam. You see, well, on the population level, again, thresholding is not so bad, and but emphysema seems to be slightly more correlated, and that's confirmed by the numbers here. But at going to, again, the individual level, if you want to really follow the individual base increase in or progression in emphysema over time, and here this is comparing also for doing this evaluation for normal subject and for disease subject. Well, you clearly see on the blue lines here that you get a steady increase and as expected increase of emphysema over time using the HMMF segmentation, and also that disease progress more than normals. While for the thresholding, well, it's not too bad if you remain in the cardiac scans. When you switch to the full lung scan and you compare personal emphysema, you see a major problem here and realistic decrease in personal emphysema. All right, so once we had this segmentation tool, then we were ready to do domain adaptation and what we call unsupervised domain adaptation with adversarial learning, UDA. So the idea here is that we work with two domains, a source domain and a target domain. So the source domain is are those synthetic cardiac scans that we generated by just downsampling the full lung CT scan. And the target domain are all the real cardiac CT scans that we had. And equipped with that, you can feed those RRIs to three neural networks. The first one, which is the feature extractor, which works on both source and target domain. Then we have a second network for the image classifier, which works on the ground truth labeling that we have for this source domain, and a third neural network, which is the domain discriminator, and which evaluates, which tries to discriminate between the two domains here, the synthetic scans and the real cardiac scans. And the loss functions then is a balance between the classification loss and the domain discrimination loss with this parameter alpha. So, oh yeah, and I forgot to mention that it didn't work immediately, and we were at some point a little bit desperate on why it was not working. And actually, one of the key things we have really to pay more care than we thought was on the sampling of the ROI. So, and this is all explained in the paper, but basically we ended up with really paying great attention to where we were sampling for the same subject on synthetic and real cardiac scans, so that they would be in good correspondence. All right, so the data we worked with is detailed here. So the split for the training, validation, and test set was based on the full lung CT scans available in the MESA exam 5. And once we had split our subjects into training, validation, and test set, we applied, we selected the same subjects and their cardiac scans available across the different generations of exam from 1 to 4. And the good thing is that we are lucky enough to have enough samples that we were able to distinguish training for actually 3 target domains, which are helical scans, MDCT scanners, and EBT scanners. And you have the numbers here. And as you will see in the results, that was really key because actually those target domains are really different and really benefit from having a UDA trained specifically for them. So how did we evaluate the UDA framework and the quality of the labeling of emphysema subtypes on cardiac scans? The first thing here is that we looked at, so just focusing on the synthetic cardiac RI in exam 5 compared to the real cardiac RI in exam 1 to 5. What we looked at, so this is really at the RI level, what we looked at are 2 things, the what we call the accuracy and classification. So that's the SLTP classification accuracy on synthetic RI, and then the domain accuracy, which is the domain classification accuracy on real versus synthetic RI. And here we compared UDA to the alternative approach to see the effect of this domain adaptation. So, and what we call CNN here is just using the first 2 networks without any domain discriminator encoded in NN3. And the last thing I'll mention here is this alpha max was optimized and determined by maximizing this accuracy, total accuracy, which is the accuracy of the classification minus the accuracy of the domain discrimination. And this minus here, I didn't mention that, but this minus here is important because the whole goal and the whole concept here is that you want to work with features that are invariant in domains, so that are not capable of being a good, training a good discriminator between domains. So at the RI level, validation accuracy for SLTP labeling and domain classification in MESA exam 5 led to the following. And 2 things that we learn here. So if you look at the classification accuracy, what we can see is that we get adding a domain adaptation to the labeler, pipeline, leads to a slight decrease in SLTP classification accuracy, using again our supervised ground truth cohort. On the other hand, regarding the domain adaptation, we can see here that the UDA, so again, the lower the better, has a much lower and so much better domain discrimination accuracy for what we want to do. That alpha max varies a lot across target domains, and that if you were just using the classifier features to do domain discrimination, then it does a much better job. So, which is against what we wanted to do and use again the domain invariant features. All right, so moving on, we then evaluated the SLTP labeling in MESA exam 1 to 5 at the individual level. So to do that, we did 2 things here that are summarized in this table. First, we compared the labeling using the synthetic data versus real cardiac scans that were available for the same subjects. And this is again distinguishing the 3 target domains. And then we moved to the just comparison of 2 real longitudinal cardiac scans, where we identify the target domains as for baseline and follow-up. And here you see there are pairs of cardiac scans where there's no domain change. And here, finally, the pairs of follow-up baseline and follow-up where there was a change in the scanner type between the 2. So this gives you an idea of the number of subjects available, the number of SLTPs detected in those scans. So not always the 10 SLTPs are being labeled. And finally, some 2 metrics, so the chi-square distance between the SLTP histograms and the correlation value between the person SLTP in the pairs of scan. What is in bold corresponds to significantly better performance, and basically UDA wins. So domain adaptation, confirming that domain adaptation really is beneficial in what we are trying to do, and leads to higher correlation here. And also here, especially, so one of the great gain was when there is a scanner type changes, as seen here, where we both improve the correlation between SLTP, percentage of SLTP, and the distance between the SLTP histograms. And this was done, on pairs of MESA acquired within a limited amount of time, so that there shouldn't be too much progression and too much changes in the SLTP labels. All right, and the last thing I wanted to mention, this is a short study we did last summer, where we actually went back to thinking about, you know, could we try to do other things with those cardiac scans, like, for example, super resolution, or really some mapping between full long CT scans and cardiac scans. And for that, again, what we are really missing is the apical part, because without this, we can't equip the lung with any spatial coordinate, and then mapping becomes very difficult. And so we did this small experiment that I wanted to mention to you today, which is using GAN to infer from a cropped view like this of the lung mask to infer the full mask. And those are illustration, you know, of typical results we were to obtain comparing to the ground truth, which is here. And that was actually pretty easy to train, and this led very quickly to you know, good visual results. One of the tricky part was actually to figure out a good thresholding, as we were generated non-binary maps. And this is where it took a little bit of time on the validation set to come up with the best thresholding strategy. But overall, the DICE score are very high, either for training, validation, and test set. And so that's the strategy we might pursue in the future. And I have to say, even if it looks like a simple, basic study, the clinicians would find also a lot of interesting options by having such tool. So now I will conclude in two parts. First, what's next? Well, basically with the renewal of our NIH grant, we are now looking at what we call deep and molecular QES. We're working with the latest generation of MESA exam called MESA exam 6. And with that, we are first now looking at adding some temporal regularization in the labeling of our QES. Then we will move toward deep QES by adding information from expiratory and angiography CT scans now available in the MESA cohort. And then moving on from deep QES to molecular QES by adding genetic information. And this is all, again, still evaluated via association with clinical symptoms. The second nice things that we are moving toward is to use now a new cohort called CanCohort, coming from Canada, as a replication cohort for all our learning process. In the second part of the grant, we looked at explanted lungs with micro-CT, which is the GRAL, basically, as you can then confirm what label QES has seen on CT scans really look like when you look at the tissues. And finally, the third goal is to go into the clinical world and translate our quantitative emphysema subtype on low-dose clinical scans. In parallel, we're working now still in the concept of unsupervised learning into quantitative airway tree subtyping. And the goal here is to understand the role of variance as seen in the general population in COPD. The second thing, part of my conclusion, is on lessons learned that I wanted to share with you, and in particular with the young audience today. And as a first message, I would really encourage you to discuss your method with clinicians as often as you can and learn to speak their language. This is an invaluable resource. Clinicians are usually very happy to discuss methods, results, and strategy to evaluate your results. And also, this is absolutely mandatory to really work very closely with clinicians if you want to write any grants, such as for the NIH. Know your data, so in particular, know the physics of imaging when you work with medical imaging. And on the other hand, don't assume too much regarding consistency in imaging, in particular when you're working with very large cohorts and with CT scans that evolve a lot in time. Ancillary studies and proposals can be an asset rather than a nuisance. I actually find it now very interesting and useful to agree very much ahead of time and on paper on what we want to do, using what data, what kind of method, and what kind of evaluation to use. And the other nice thing is that when you work with MESA and Spiromics, you're really part of again a big community of investigators that work on the same data. So, and when you get feedback from the committees reviewing your proposals, you usually get very interesting feedback, and also you know that everybody is aware of what you are trying to do, and that you're doing something that is different from other people. Finally, small tasks such as measuring percent of emphysema or registering cardiac scans, which I didn't detail today, but we had to do at some point, are not always easy, even though they sound simple and basic, and they can take you a very long way. And this is what happened to us last summer, where we were included in a big JAMA paper studying the influence of air pollution on emphysema and lung function, and where basically our measure of percentage emphysema with HMMF was used as a replication measurement compared to thresholding confirming findings in this paper. Finally, dive into unsupervised learning. I hope I've convinced some of the people in the audience that this is an interesting adventure, even though it's very risky and it can sound frightening, because again, you have no idea of what you're looking for and what you're going to discover. But clinicians do, I think, rely on us to make really great progress and impact in subphenotyping disease, and that's basically the only way we can do that. Deep learning requires human intelligence, and especially when feeding the data. And that was really one big lesson to us when we worked with the UDA framework, that we had to pay more care than we were doing when sampling errors from the target and the source domains. A 10-year research cohort is heterogeneous, definitely, but that's nothing compared to clinical heterogeneity. So keep always that in mind when you're trying to be, too specific to a specific research cohort. And finally, I'll take this opportunity to ask reviewers in the audience that when you review unsupervised learning, be open-minded, because again, this is really challenging and this is really difficult. We were lucky to have a fantastic cohort of data to do this kind of work, but not everybody has access to such data, and they are still, I think, very valuable unsupervised learning strategy to investigate. And finally, acknowledgements. All this work was done in the Hefner Biomedical Imaging Lab at Columbia University, directed by Andrew Lane, and most of the work was performed by 2 PhD students, Ji Young, who is now at Google, and Hiro Hammer, who worked initially on the HMMF segmentation framework. Thanks also to all the other students here who did some portion of the work. This was done jointly with Columbia University Medical Center and Graham Barr, who's the PI for the MESA and Spiromics acquisition at Columbia University, and some people of his team and collaborators who provided especially all the association with clinical symptoms. And external collaborators involving University of Iowa, in particular Eric Hoffman, and University of Virginia for the GWAS analysis. Again, thanks to NIH for funding this work, and thanks to the MESA and Spiromics committees for supporting our work, being positive on all proposals we've submitted so far, and having always very valuable feedbacks for us. Thanks for listening.